So the Factorio project is a brainchild of a few of us. About 3 years ago, we came up with this idea of applying optimization within the video game Factorio for the purpose of, well, various things, simulating real world problems, satisfying our personal curiosities as to whether we can be replaced as humans within the video game, as well as seeing if certain optimizers are more efficient, and testing our own software development skills and finding out if it's possible to actually connect external optimizers into the video game Factorio. This then grew arms and legs, and we've now created this rather large framework which allows people to connect to Factorio without learning any other languages. It's a standalone framework you just install, and you can then connect into Factorio and start solving problems without anything except for your own programming language and your own solver and this framework, which is excellent. This is still being developed. We're at a stage now where some of the problems have now been defined and added. And Patrick's going to be actually showing some work into one of the problems that he has introduced and solved as well within the Factorio learning environment. This project is always looking for collaborators. So if you are at all interested in doing some work on the Factorio project, please do not hesitate to get in touch. My email is readken1@msu.edu, and we're always looking for people to come join in because this is an unfunded project, so we do it for fun in our spare time. So any collaborators are always welcome. Okay, with that, I've now turned on sharing privileges. So Tom, Patrick, Payam, you should all be able to share your screens now, not at the same time. Let's begin with, let's go alphabetical order between Patrick and Tom. So Patrick, do you want to go first?
Yeah.
Okay.
I can go first. So
great.
We start the presentation. Okay. Can you guys see the screen?
Yes, I can see the.
Yep. Okay, so I worked on the electric pole placement problem, and yeah, let's start into it. So first of all, I have a table of contents. First, I talk about a few basics for the problem. Then I talk what the electric pole placement problem is exactly, the implementation, the evaluation, little summary, and outlook for future work. So the first basic we need to talk is the set cover problem. Some of you might already heard of it. It's a NP hard optimization problem where you have a set U that should be covered by a combination of subsets of U that have the lowest cost to it. One example would be a U of 1, 2, 3, 4, and 5. And we have 3 subsets, S1 to S3. And if we want to cover U with those subsets, one optimal coverage would be S1 and S3 because they have all elements in them. A logical approach for the set cover problem would be a greedy algorithms. So you would iteratively select the one subset with the best cost effectiveness, and then I continue with the next one. Yeah. And then we have to talk about the game Factorio itself. So Factorio is developed by Whoops software. In Factorio, a player crash lands on an alien planet and can build his own Factorio complex. The end goal of the game is to launch a rocket into space and to escape the alien planet. And in Factorio itself, there are many potential optimization problems. For the electric pole placement problem, the behavior of electricity is very important. electricity is generated by a power source, for example, a solar panel. It can be routed through power poles, and each power pole supplies a specific area with electricity. You can see this in that image here. The solar panel generates the electricity. The power pole covers the solar panel, so it takes the electricity of the solar panels, routes it to the next power pole, and in the area of the next power pole is a laser turret that can use the power from the solar panel. So the electric pole placement problem, you start in an initial state in an area of any size with randomly placed machines that need power. For example, at this one, you have a already placed solar panel and an initial power pole, and the randomly placed machines that all need electricity to work. The goal of the electric pole placement problem, or short EPPP, is to connect as many machines as possible to the power grid by using as few power poles as possible. And that is very similar to the set cover problem. The set U would be, in this case, all machines that can be connected to the power grid, and each possible power pole you could place is a subset of U that introduces a few machines to the power grid. And for a later method, the terminal state is also important to define. A terminal state would be to connect all possible machines to the power grid. That would be an example of a terminal state. Interesting for this example is that the machine in the middle of the picture with the yellow icon is not connected to the power grid because all the other machines around it blocks it from being connected by one of the power poles, and so it cannot be connected to the power grid itself. Okay. The implementation, first thing I implemented was a fitness function. That should consider the following aspects: the number of electrified machines and the number of power poles placed. A general form of the fitness function would be W1 times V minus W2 times C. The W's would be rates, and V would be the number of electrified machines, and C for cost would be the power poles that got placed to connect the machines. For my algorithms, I used this form. So I gave the number of electrified machines 10 times more importance than the number of power poles placed. When, for example, you have a machine that is very isolated from all the other machines, and you need, say, let's say 3 power poles to connect to the power grid. With this fitness function, that would be possible because that one machine that would be connected to the power grid is 10 times more important than one power pole placed. So the algorithms I used, so yeah, for finding solutions, I used local searches and genetic algorithms. The local searches can be divided into 2 different kinds. The first kind, but for the first kind, an action is to place or remove any power pole in the area. So here you have the initial state, and an action would be to place a power pole here, place a power pole here, or here, or here, or remove any power pole that already got placed. One of the methods I implemented was the greedy set cover search. That's the greedy algorithm for the set cover search, set cover problem. I talked about a few slides ago. I also optimized the greedy set cover search by ignoring positions that are too far away from the last place power pole. And our problem with a greedy search is our local optima. To fight against that problem, I used two different methods. First of all, I implemented simulated annealing to fight local optima, and I used a combination of the greedy set cover search and taboo search. And taboo search is a meta-heuristic. We use a taboo list, and you when you visit a state with your greedy search, you place that visited state in the taboo list, and it's for now forbidden. So you don't visit states twice. And if you are in a local optima, you have to go out of the optima because the state you are in is already forbidden. So you have to move on. And so it tries to search more space and tries to flee from a local optima. I also try to optimize this combination by ignoring the positions that are outside the connection range of the power poles that that already got placed. So the second kind of local searches have the following actions. The moving and removing of power poles that already have been placed is allowed. So you start with a random set of power poles, and you can't place any more power poles, but you can move or remove the power poles that are already there. And that are the movements that are allowed. So you start with with one of the initial power poles, and you can move it diagonally, up, down, left, right, and remove it. So 9 actions per power pole are allowed. Here I implemented a greedy hill climbing algorithm and simulated annealing. The last method I implemented are genetic algorithms. And there I implemented a rather generic approach, and the approach that were specifically developed for the set cover problem with the sources here. For both of these approaches, the following applies for both of the genetic approaches. The algorithm starts with a randomly generated population. The genetic material is represented by a bit string. Each bit represents a free position in the area of the EPPP. A 0 means the position remains empty, and a 1 means the power pole is placed on that specific position, or a power pole is placed. And upon completion, any excess power poles will be removed in a random order, because sometimes there will be a few power poles that are left that don't really affect the fitness function in a positive way, and you go randomly through every power pole and see if it has a positive effect on the fitness function. If not, it gets removed. So the properties of the generic approach are: the population change is via a generational approach. So a new generation replaces the previous one. The selection is in the selection we choose the parents through an interval of all fitness values. So we have an interval with every fitness value added to it. So it's more or less an interval from 0 to the sum of all fitness values. You take a random point in it, and the corresponding individuum is then chosen as one of the parents. The recombination is implemented via a crossover with a random crossover point. And the mutation, in the mutation, each bit is inverted with a probability of 1 divided by n, and n is the length of the bit string. So the in average, for every mutation, 1 bit of the bit string is inverted. for the approach for the set cover problem, the properties are a bit different. The population exchange is happening with each individual, each single individual. So each newly generated individual replaces another one in the population with a below average fitness. By the selection, the parents get chosen via a tournament selection. By the recombination, each bit so for the recombination, the bit strings of both parents get sorry, I need to find the right words.
Don't worry, Patrick. Your English is a lot better than my German, as we saw. Take your time. Are you just trying to define recombination?
Huh?
Are you just trying to define recombination?
Yeah.
Okay, recombination is when you have well, you say it there. Each bit is determined at random based on the fitness of the parents, and you I think that's fine. You can continue on from there.
Yeah, it's a special form of recombination. I just googled the word. So you compare each bit of the bit strings. If they're from both parents, if they're equal, you just use the same bit in the child. And if they're different, you chose one of the bits based on the fitness of the parent. So if parent 1 has a higher fitness, the bit of parent 1 has a higher chance of going into the child. So and every recombination just makes one child instead of recombination by crossover, which gets 2 childs. So the mutation is instead of a static probability, it's dynamic. It gets calculated with each individual, and it changes as the algorithm progresses. And it's not a probability in and of itself, so it's a rate. So if the calculated rate is 2, every mutation, so 2 bits get inverted 100% of the time. So it's a static rate, not a probability of mutation. So let's get to the evaluation of the implemented methods. We have a few examined scenarios for this. At first, we have an area of 12 by 12 with a high density of machines in it, and with the short name 12x12h. Then we have also an area of 12 by 12, but with a very, very low density of machines. And we have areas of 24 by 24 with a high and very low density of machines, respectively. And for each of those scenarios, each algorithm runs 50 times in this evaluation. The important properties that got checked for the evaluation were the average fitness of the found solutions with average fit, and the average runtime in seconds for the solution to be found. And a few remarks: both generic algorithms stops after generating 1,000 new individuals, and the taboo search I talked about earlier, which extends the greedy set cover search, extends the optimized version. So the optimization I made for the greedy set cover search, it extends this version of the greedy set cover search in the evaluation. So first of all, the measured fitness values. So for the 12x12h scenario, most methods have found round about the same fitness, except the hill climbing and the simulated annealing from the local searches of the second kind. So local searches where you don't place new poles, but just remove or move already placed problems. Those have severely worse fitness values in this scenario. For the 12x12g scenario, it's a bit more mixed. The local searches of second kind are already pretty bad, are also pretty bad. Here the 3D set cover search and the optimized version are the same. The extended optimized version of the secret cover search by a taboo search and the optimized version of it are a bit better. The genetic algorithms are also pretty good, and the simulated annealing from the local searches of the first kind is relatively bad. By a 24x24h scenario, it's nearly exactly the same as the 12x12h scenario. So every method is round about the same, except the local searches of the second kind. And with the 24x24g scenario, it's also a bit more mixed. But you can see the greedy set cover search and the optimized version of it are pretty much the same. The optimized is even a bit better, even if the optimization should only really affect runtime. Simulated annealing was a good amount better, so probably there were more local optima with the greedy set cover searches. The extension with the poo search and the optimized version of it were the best. The local searches of the second kind were also not that bad, and the genetic algorithms were also pretty decent in the found fitness. So now the evaluation of the runtime. Here, the first scenario, 12x12h. You see most methods have a pretty low runtime, but the genetic algorithms have a very high runtime. The reason for that is that the genetic algorithms always generate 1000 individuals, and if the solution is already found after 100 individuals, it's not stopping, it's producing 900 more, or generating 900 more individuals. So the runtime for 12x12g, here also the genetic algorithms pretty bad, but besides that, it's you can see that also simulated annealing from the local searches of the first kind is also a good amount worse than all the other local searches. The 24x24h scenario has a bit more of a mixed environment of runtimes. The highest runtime is the greedy set cover search. And now you can see what the optimization of the greedy set cover search made for the runtime. For the scenarios with the lower area, it doesn't really change anything. But if you scale it up more, you can see it's nearly halved the runtime for this scenario. For this scenario, simulated annealing has an even lower runtime, and the extensions via taboo search have that are based on the optimized version of greedy set cover search have a slightly higher runtime, but not as high as the greedy set cover search. The hill climbing from the local search in second order have also a pretty high runtime. In contrast to the simulated annealing from the local search's second kind, which has the lowest runtime for this scenario. And the genetic algorithms are pretty have a pretty average runtime for this diagram. And now the last scenario, again, 24x24G. Here you can also see that the runtime from the optimized greedy set cover search is also a bit better than the not optimized version. Simulated annealing is here a bit worse than the greedy set cover searches, and the extension via a tabu search is a good amount higher, and but the optimized version saves a bit of time by this one, in contrast to the 24x24H with where the optimized version even has a higher runtime. But I think that's more of a few outliers that got the higher runtime here. The hill climbing from the local searcher's second kind has the highest runtime here, so it's very ineffective because it also has pretty bad fitnesses. And the simulated annealing, in contrast, has the lowest runtime here. And also the genetic algorithms are pretty average again. Okay, so the summary of the electric pole placement problem. First of all, Factorio is a video game with many possible optimization problems. The EPP aims to connect as many machines as possible to the power grid using as few power poles as possible. Many different optimization methods have been implemented, and in the evaluation is seen that both the local searches of the first kind and the genetic algorithms performed similarly well. The local searches of the second kind have most of the time the worst fitnesses, and hill climbing has a very high runtime, and simulated annealing has a relatively low runtime, but because of the worse fitnesses, it's not really a good solution for the problem. And now at last for the outlook. In Factorio, there are several types of different power poles. For this problem, I only considered the small electric pole or a small power pole, but there are 4 different power poles. So for future work, someone could implement the possibility of every power pole to be used. And because of the rather high runtime, it's needed to find a solution. If we go back in the slides, you have here for a 24x24 problem with a high machine density, which isn't really that big of a problem. You have around 2000 or 1500 seconds for each problem, and that's half an hour or nearly half an hour, and that's just too long to optimize a rather small area of machines to be used in the game itself, for example in a mod. So I would say it would be a good consideration to implement machine learning and maybe train it with the solutions found with the best method here discussed. Okay, then here are my sources, and thank you for your attention. Are there any questions?
Thank you so much, Patrick. There is one question in the chat I'll read out. So this is from Josh. He said, did you evaluate if the network formed a grid connecting power source to all power consumers, or instead just if the consumers were near enough to a pole?
No, not near. Also I evaluated that the machines got connected to the actually a solar panel, to the power grid. I used a function for that to check every machine if it has access to electricity, and if so, it gets counted as an electrified machine. So it's not just if it's near a power pole, it's if it has really the power itself.
Excellent. And that's another point about extensions in the future. You can actually have separate power grids. You know, you can, and that's another thing we have to consider at some point is we have to make sure that they have enough power as well. But that's a separate problem. And Josh also asked, did you penalize greedy algorithm or genetic algorithm organisms with too many poles, since you said that you pruned the worthless ones?
No. So that's the reason I pruned the worthless ones. So I didn't penalize it. But would be a good idea. I didn't think of that.
Yeah, one of the things we wish to do at some point is so the fitness function right now is a really good start. We want to also add in some additional considerations to the fitness function, including things like aesthetics. So we're going to be because right now it'll place them wherever it can to make sure that there's a feasible solution. But a nice soft constraint would be if we had it set to try and have some sort of orderly grid to ensure that future problems and solvers have an easier time. Maybe that's an assumption I'm making, but at least when humans try to solve the problems, it's easier to have a kind of orderly solution so that you can have easier solutions to other problems in the future. Much like organizing things in your office or whatever into correct folders, into correct storage containers. It's the same in Factorio. Having correct spaces for specific things can be potentially useful for reducing problems in the future. But again, all out of scope and useful, interesting future stuff. Tom, you have a question?
Yes. So is your fastest algorithm faster than me, than the average player at placing poles?
Can you repeat the question? I didn't understand it correctly.
For one of your scenarios,
yeah,
is your faster algorithm faster and better than the average player?
I can say that I don't have the data to say how good an average player would place the power poles.
I think we can safely assume that this is going to be slower than the average player at the moment. If the average player has played the game before. I mean, if it's me, I can probably solve the problem in 3 seconds, right? Because I've played the game a lot. But if you took my father, who has never played the game, maybe the algorithms would beat him.
Yeah. Okay.
So I would say it's definitely slower, but for a bigger problem area, I think the algorithm would be finding a better solution.
Okay.
That's a good point. Okay, thank you, Patrick.
Also when I started, so this is all part of my bachelor thesis. When I started writing the thesis, I thought I could implement machine learning right away, but then I had a problem of where can I get my data? So randomly generating the problems is maybe fine for it, but then where do I find good solutions? So I
may have a solution for your lack of data problem. Blueprints.
Yeah.
Yeah,
Not-
there is a huge database of player-made blueprints of different kind of factories. So which power poles on them?
That's actually a pretty good idea, because I think most of the blueprint creator really strive for the optimization.
Yeah,
And
there are few trolls, few dumb stuff, but this is part of the fun of AI.
Absolutely.
Yeah.
Okay, thank you very much, Patrick. I realize that we're quite far through the meeting already, and we still have 2 more presentations to go. So
Yeah.
thank you so much. That was an excellent presentation. And
Yeah, thank you.
Tom, can you go next?
Yes, I'm gonna start sharing. Can you see my screen?
Yeah, I can see it.
Yes.
Okay, so we're gonna talk about blueprint analysis in Factorio. But first, I'm gonna introduce myself quickly. So I'm Tom. I'm from France, and I've just graduated from my 5 years of computer science study. And I'm actually an engineer in computer science. I don't know if it makes sense in the US, but that's my title. So my main skills are into the development side of web apps, and I have some DevOps skills also. So I'm not into the scientific field, so you won't see any fancy formulas because I don't know how to read or to write them. But I enjoy doing some algorithm and music, 3D printing, and of course, video games. And you can find my personal projects on my website. So the table of contents. So I'm gonna explain what is a blueprint, what do we want to analyze on it, why is it useful. I will tell you about the scope. Then I will tell you what my algorithm is doing, what are the steps, then show the results. So what is a blueprint? So a blueprint is something that a player can make in the game. So for example, here in the game, he can create a factory, then copy paste it and export it in a string, in a text format. This text can be decoded into a JSON, and that's basically what the game does. You can see on the left an example of a blueprint. It's basically a list of entities with their coordinates and directions, and that's enough for the game to place it back on another world. What do we want to analyze on them? So we want to find what was the creator intentions, where are the inputs and the outputs of the blueprint, and first of all, if it's usable blueprint with the supply chain, because what interests us the most is supply chains, even if we can make some logistic or trains blueprints. So we want to avoid them. So we want to see where are the inputs and what items are supposed to be put on those inputs, and what items are supposed to be exiting the supply chain. Apart from that, we are interested into the efficiency of this blueprint. So how much items will exit, how much items will enter, and what are the usage percentage of each entities. This information will help us see where are the bottlenecks. So what are the entities to upgrade to make our factory faster. So the challenge lies in the fact that none of those informations are in the blueprints. It's to us to calculate them according to the list of entities. So why is it important, or how can it be helpful for us? being able to sort, to see if a blueprint is efficient, it can help us look at the huge database of player-created blueprints and sort them by ingredients, by created ingredients, by efficiency, by size, and so on. This huge database can help us do some supervised training, for example. But having an algorithm that can tell if a blueprint is good or not can help us do some reinforcement learning or some evolutionary algorithm by helping in the score calculation. Also, this algorithm can be helpful for the player with an in-game blueprint analysis by, for example, creating a mod or by creating a web app in which the player can post their blueprint and it will show him where are the bottlenecks and how much items it will be produced. Quickly, in the state of the art, some tools already give the quantity of item produced, but they only look at the recipes on the number of assembly machines. But they don't tell, for example, if there is a yellow inserter that is too slow to move the items. Those tools can't say that they won't be able to see it, and so the output will be wrong basically. So here we want to give the correct output. What about the scope? So we are I'm gonna focus on every blueprint with every kind of inserters, belts, splitters, assembly machines, underground belts, and chests. I'm gonna work with any recipes as long as there is only one output item for each recipes, which is 99% of the vanilla Factorio recipes. And I am also focused on take in consideration the capacity of the inserters, which can be upgraded with research. It's very important because changes these parameters has a huge impact on the efficiency of a blueprint. But I will ignore mods. I will also ignore furnaces, code turrets, and science. Basically, any entities that can accept items apart from the one I've listed below, to the top. I will ignore fluids modules such as efficiency modules, speed modules. I will ignore power because some other people are already working on some power placement. Trains and logic, I will also ignore, and filters. So on the right, you can see pictures of compatible blueprints. And those are basically what I work with. So what about the internship, the mission? So my goal is to create an algorithm that will be able to provide the efficiency and the bottleneck of a blueprint. So this algorithm is made in Python after discussion with the team because it's a language that everyone is familiar with. And my algorithm does what it has to do with 4 main steps that I will describe now. So first of all, we need to read the blueprint. So after someone created a blueprint in game, it can export it in a text, then give it to the algorithm. And the first thing I will do is to place each entities from the list into a 2D array because I can't work a lot with lists. Having a 2D array will be much more helpful to look at the interactions between each entities. So this is the first thing I do, and I did a nice display. What you see on the bottom right is what the algorithm display for the above example. After that, from the 2D array, I make a node graph So the 2D array helps me see the interactions between child's and parents' entities. So we can see that a belt can give items to another belt, and that an arm, an inserter can take items from a belt to drop it in an assembly machine, and so on. And I do also a little optimization to avoid having many belts in my node graph. It doesn't change anything to the output. It's just clearer and also faster for the calculations. So this was the easy part. It was very tedious and it requires a lot of tests because I didn't know for sure how the splitters works, for example. And I had to check the distance of underground belts. I'm basically doing what the game is doing. After that, so this is the end of the easy part. Now, the third step, before it's one step before calculating the bottleneck. What I need to do is to find out what entities are supposed to transport what items. Which items will be moved in each one of the entities. So how am I doing that? Do you see my mouse cursor?
Yes.
Yeah.
Okay, great. So here we can see the results on the right, and I see that the input will be iron plates, and the output will be transport belts, because it is what is being produced by the last assembly machine. So some are easy to guess. For example, I know that my recipe is transport belt, so they only produce transport belt. So I know that the output will be obviously transport belt. Same thing for the gear here. But and then for the gear, I know that there is only one input, which is plates. So I tell my parents that they are supposed to bring me plates, which is what they are doing. So it is great. But the challenge was when there is multiple ingredients. For example, the last assembly machine requires plates and gears. But here in my results, I'm asking these parents only for gears, for plates, only for plates. But it could have provided me gears too, plates and gears at the same time. So it is a possible outcome. So this is what I'm guessing. It could be in reality anything. But because I know that one of my parents is giving me gears already, I'm supposing that this one will give me plates only. And this is how I guessed which entities give me which items. It's quite reliable, even for large blueprints with many items. For example, it's quite a challenge for assembly machines that requires 4 or 5 different ingredients with 3 parents. How do you do that? Well, it has to be done. Then the last step is to calculate the usage of each one of the entities that allows us to calculate the bottleneck. So with the help of which items each entities are supposed to carry, I could calculate that. So you can see on the right the result. I have a percentage of usage for each entities, belts, assembly machines, and inserters. And I have highlighted in.
And apparently that's an early end to Tom's presentation. I assume he's been disconnected. We'll just have to hold on for 2 minutes. Does anybody have any questions or comments so far? Oh,
He was mentioning that these are. Sorry, can you hear me?
Yes, we can. Yes.
Oh, I was just curious about the if there was like an artifact being released as a result, a plugin for the blueprints that helps the analysis that he's talking about, or what?
Well,
can you hear me again? Sorry.
Yes, we can hear you again, Tom. And Jory actually had a question for you.
Yes. What is your question?
Oh, I was just idly curious about if you were working on releasing an artifact for as a result of the project, a tool that is useful for the analysis for the player to help the player understand.
Of course. So I can send on the chat the link of the GitHub project. So it's open source and with an installation guide. There is few stuff to upgrade, few fixes, but yeah, it's open right now. The usage is not the best one because you need to copy the blueprint in a file. Then when you run the algorithm, you ask for which file. But yeah, this is why I want to make a web app that uses the algorithm and with a nice graphical interface.
Ah, I see. Okay, thank you.
So that's basically how so to calculate the usage, I'm doing a flow algorithm. This was by far the most challenging part. There is one challenge. This is when there is multiple ingredients for a recipe. So my first idea was to do like Factorio does, to push ingredients, to push the requested ingredients in the parents and to watch the ingredients flow through the blueprints, through the node, the graph. But there was a problem when there is multiple ingredients required. For example, if I push ingredients here, I push ingredient A. The assembly machine can't tell me now, of course, how much it can output because it doesn't know yet how much ingredient B there is at disposal. So by starting from the start, my thread from my recursive algorithm must go backward. It must stop there because it can't know how much item will be produced. But when we do item B, then now we know how much items there is that there can be produced, and we can output. But if the bottleneck is after the assembly machine, which is the case here with this the last inserter, then the outputted item, the provided item in this belt, the A item, it can't be updated. So basically, it gets wrong. So I don't know if I'm clear. It's hard to tell in a few minutes what the problem was, but the solution was basically to instead of pushing ingredients, it's to push a request. So we start from the end. And for example, here I know that the output is belts. I'm outputting belts, so I'm doing a request of belts at the maximum capacity of this node, which is 16 items per second. Then it goes to the parent. It gets reduced here because the inserter has a capacity of 1 item per second, and so on. And because I know there is always 1 item output for each recipes, then I don't have the same problem. I can wait here for each one of the parents on the same thread. Some other solution could have been to create a database or do some multi-threading, which would have been more complicated. So this is basically how the bottleneck was calculated. And the last part is to output the results. So to do that, I've chosen to enhance the input blueprint. So I've completed the given blueprint with the data that I have calculated. So for each one of the entities, the usage rate, if it's an input or an output, if it's a bottleneck, on which items will be transported at which rate, at which items per second. And I also output for all the blueprints, not for each entities, the amount of item inputs, of item outputs, which entities are the input of outputs, and which entities are the bottleneck. So the item inputs, which entities are input and output, are very, very interesting, because basically I could create an entire Factorio world that can launch rockets only by looking at public blueprints and by placing them randomly in the world, and by linking the outputs of the blueprints with the inputs of other blueprints, I can basically launch a rocket without placing any assembly machines, only by looking at public blueprints. So this is a result with a larger blueprint. And we can see on the left that there is 4 entities at 100% usage. And there are the assembly machines that produce the pipes for the underground pipes factory. So here, to increase the underground pipe production, which is currently at 1 underground pipe every 2 seconds, I need to upgrade those 4 assembly machines, or add more of them. The algorithm is available also on GitHub. Thank you, Ken, for sharing the link. It also comes with a set of 58 blueprints that allows me to have a 70% coverage. The rest of the coverage is mainly some graphical stuff that I'm not testing. However, there is some issues with the algorithm at the moment. It's fast for single blueprints. It's like very, very, very fast. But for some reason, due to Python or something I don't understand, the more I use it, the slower it gets. There is no memory leaks. It's just some codes take longer for some reason. I have no idea why. Also, the older blueprints aren't supported, and I'm not checking the versions of the blueprints. So if you take an older blueprints online, it may not work. Only the latest blueprints will work. What about the next steps? So note that we can find bottlenecks in blueprints. So we could, of course, upgrade the algorithm to increase the scope and take mods recipes into considerations, take in consideration furnaces, fluids, modules, and fix the few issues there is. But we could also start a new project with this algorithm, which, for example, creating a web app that uses the algorithm to help players with their blueprints. As I told you before, creating a dataset of blueprints, making a reinforcement algorithm or an evolutionary algorithm. I say that it could also be integrated into the Factorio interface. I don't know how, but maybe it could help by creating automatically some, or upgrading automatically some a world. And that's it. That's it for me. Thank you very much. I don't know if you have some questions.
That was fascinating, Tom. Thank you so much for sharing. Yeah, does anybody have any questions?
I have a question, comment. Yeah, what would you recommend to a future student, intern student, who is working on Factorio similar to this? What would you give them words of wisdom?
In practical, I had troubles with running Factorio on my very small computers that I had to because I could not take my big computer for the internship. So I bought myself a Shadow PC. It's an online PC that allowed me to play Factorio remotely and create the many blueprints that I needed for my test. And it wasn't easy to transfer them, but it worked at the end. So I'm glad. Some other kind of tips are, I don't know. Decide your scope very early, because there is many things that can be optimized and that you can do.
Okay, thank you, Tom, and thank you for the question, Jory. Any other questions? Patrick?
Yeah, Tom,
Yes.
when I use your tool, would I get actually this nice node tree that shows me with colors where the bottleneck is, or?
Absolutely.
Huh?
Let me share my screen. Okay, I need to run the algorithm again. Okay. Do you see my screen?
Yeah.
So I've just started the script. En fait, it's open internet tab with the node graph, and you can see the results here. So this is the basic example, the most basic test.
Nice.
But yeah,
Looks
this
good.
is, so it's funny. It's very funny, but it's hard to see. So here I see that this inserter is the bottleneck, but it's hard to look in your blueprint where it is, because it can be anywhere. Yeah. And it's very, very complicated on a very large blueprints to see which inserter is where, which is it's funny at first, but it's a limitation. I think it could be done better, maybe by recreating the blueprint.
But Tom, I think Patrick's also asking, how did you generate this graph?
So I use a library. It's PyVis. I think it's PyVis. It's just a basic Python library that allows me to display nodes. So just by running the algorithm, this will display. Basically.
Nice. Thank you.
Good question. Thank you. Any more questions for Tom? Okay. The one thing I wanted to bring up was, Tom, I looked at your GitHub, and I did a couple quick pull requests of typos. FYI.
Thank you.
And I should have done it before the presentation. That was entirely on me. I'm sorry, but I finally sent them off. I really liked your idea of using this as an input for machine learning and genetic algorithms and such. I think there's a lot of potential there, and yeah, I'm hoping we can find somebody who's interested in picking up your project and doing that kind of thing with it. I think that'd be great. How do you feel about making a Reddit post about your tool in particular? Because I think that the Reddit community, the Factorio Reddit community, would love to see this tool. And I imagine that if we showed some people in that community, most people will just use it as is and enjoy using it. But there'll also be a fraction of people who would want to actually develop on it and improve it, I imagine, for you. So these future works that you're talking about, I think if you opened up to the community, some of them would probably be willing to work together on this.
it's a great idea. I'm a little bit nervous about that. I was waiting for maybe creating a interactive web tool. I think it will be more easy to use than I don't know if every player that are interested have Python on their device.
Well, that's a quite good idea, actually. You could probably use GitHub Pages to make a static web page that runs using the tool pretty easily. But if you're interested in doing that with us, Tom, that's like, keep in touch and we can help with setting all that up and provide some assistance or code review.
I'd be glad. Thank you very much. Last thing, yeah, you were talking about the blueprints. I think that it will be the better way of sharing data between every component of the Factorio project. It's created by Factorio. It won't change. I'm using it, and I think everybody should take it as an input for their different algorithm. If, for example, if some algorithm are creating some factories, it should export them in blueprints, and the Factorio interface should be able to take them as input and place them in the world, for example. It could be the better way of a good way of sharing data between every component.
Okay, cool. Thank you, Tom. Okay, with that, let's move on to the final act of the show today. Payam, if you're still connected and available, I will give the disclaimer that yes, we can. I will give the general disclaimer. Payam is based in Iran, and internet connectivity is not reliable at the moment. So if there are any issues, don't be overly surprised. But thank you for taking the time to do this as well today, Payam.
Thank you. Hey everyone. This is going to be my basically presentation on and an overview on what I've carried out so far and what I've got planned for the upcoming future, and on the FLE Factorio learning environments. Let me know if you can see the page and the screen as well.
Yes, we can see the slide and we can see your cursor as well.
Cool. So I started by reading. We basically started by talking about this, and then I read the article, talked some, saw the presentation. The out of game problems and the ability to just use this game as a way to simulate different sorts and a variety of problems was really interesting to me. And we got started. I reviewed the code, and right now I'm working on the sort of problem, and I'm trying to figure out how to connect the Python to Lua. And experimenting with the code and such. There are a plethora of problems, ranging from just picking up items and getting them from one place to other, to basically launching a rocket, which is the actual end goal. And the approach I'm taking with this is to get and make different small solvers and basically provide different problems, different solvers which could be built on top of each other to I forgot that word, but basically it's just building on top of each other. And this is a set of problems which I'm currently thinking of working on, but right now the problem I'm working on is the inserted placement problem, and this is what I've chosen with the help of Ken and others as a starting point, basically. So each problem we have has different parts, and to solve them, which we need to tackle, from constraints to mathematical presentation to the fitness and a way for them to see the world, to perceive it, and to interact with other such solvers. For example, here we have the soft constraints. And I think we won't need any hard constraints on this particular problem, but the soft constraints for example, the inserter placement problems are going to be such that we could still operate, have more space to operate and to place the power pools to get the input from specified, or I think maybe later on we'll get to the point where we could figure it out. So there is no specific input, but it's going to be derived from the environment. And then it will maybe, so this is one of the ways used with the next solver, the logistic build solver, to take the resources to a place which could be then transferred to an output. And then it's going to be a specific output, an input, and we want to basically minimize the number of inserters used. And after the inserted problem, I'm going to be tackling the logistic build, but the logistic build, basic logistic build has been already solved. So it's going to be that plus a little bit of tweak, and it's going to be so maximizing what gets through and minimizing the mix-up of the different available resources without, because sometimes it just messes up things, and having the excess space for other things might be good. And one of the things that we might want to highlight is the resource lines. So the ability to detect these resources, I think, is going to come up in different places. So I'll come back to this in the mods part, but this is basically something that's I'm not sure if I should be doing it in Python or Lua, but I think it would be better to create a mod for this, or other things that are like this and are going to be coming up again and again. And next up, I think I'll really tackling the mining drill placement problem. And in this one, the solver which forgot who worked on it. I think it was Patrick. Yep. So the solver that Patrick had worked on, the power pole problem and the belts problem, are going to be the hard constraint for those, for the mining drill problem. And the soft constraint is going to be to maximize the number of placed drills, the mining drills, and or the amount of available resources covered, because it's always good to place the most number, but we might get better results if we take the actual resources that are under those drills into consideration. And after that, those mining drills are going to take basically get some resources out. And so logically, I think that it's a good thing to do the smelting design problem. It's basically the same line of thought. So we're gonna be able to detect where the resources are, place some power poles, and then, you know, I'm still not sure how to optimize this. It's what to optimize it against, but the throughputs might be a good thing to use here. So I'm not still sure about that. And the rest of the problems that I'm considering right now, I've shown them at the start of this talk. And basically, I'm going to tackle them one by one, depending on how it goes, how well it goes. And they're going to be built on top of each other. So I think the design pattern that I'm going to go for is to design small solvers and have them get and give, if needed, the fitness. So they'll get, they'll provide an internal fitness, and they'll get fitness from other solvers, depending on the type of solver they are, and depending on the nature of those solvers. And this way we could basically have blocks which reduce the need to make every solver from scratch. And there is going to be some things that are going to be coming again and again, or are going to be needed in different problems. So some of these are going to be provided as mods, which others could use. Yep, I think that's going to be it. I'll be happy to answer any questions.
Okay, thank you, Pam. Do we have any questions?
Do you think you could? I've heard of speaking about inserters placement on optimization. Do you think it could use the blueprint analyzer?
I didn't use that. Can you repeat that, please?
Do you think the inserter placement problem that you talk a little bit about
Yeah.
could use the Factorio blueprint analyzer?
Yeah, I think. I mean, this is not a. Actually, say this is not a solver per se. This is what this provides is basically the fitness function and the basics on which the algorithms are going to be dependent. Does that make sense?
That's a good point, Pam. So basically, to contextualize, you guys all work on your individual problems, right? So it's kind of hard to see the bigger scope. So Patrick solved the electric pole placement problem and provided a bunch of solvers, whereas Payam has been tasked with defining a bunch of problems instead. So he's not going to be looking at solving them so much. Maybe a simple example, maybe if he wants to. But Payam's job is basically to go in and create a whole slew of problem definitions for maybe 5 to 10 different problems, starting with the inserter placement problem. So he needs to think about what kind of questions will people who create solvers want to ask? What kind of a fitness function would they want to have be able to ask questions about? And inside the game, what kind of information needs to be extracted from Factorio out to the FLE regarding the inserter placement problem? And then for every problem that he does after that, including the furnace placement and so on.
Okay.
Thank you for your question, though, Tom. Patrick.
Yeah. So you want to create fitness functions for those problems, or?
Yes.
Okay. So for the power pole portion of the fitness function, how do you want to so you wrote a powerful space. So I think you want to reserve a bit of space for every machine that gets connected to the power grid. But how do you want to so if you have a space for every machine for the power pole, so for one power pole, it's not guaranteed that one power pole is connected to the power grid. How do you want to insert that connection to the power grid into the fitness function?
So basically, the fitness for that is going to come from another problem, or should I call it solver? Or so it's gonna come from another. What should I call it? Should I call it solver? I think. So basically, we have an inserter, and it needs to know how well the placement of all of the machines are. So what it does is it calls the power pole solver, is what I'm going to use for the time being, and it provides it with the problem and asks, okay, how well is this doing? with respect to your problem. So it's basically going to ask the fitness of this situation.
Mm. Okay.
So it might need to I'm still not sure about this, but it might need to basically calculate some sort of probability or fitness of its own and just give it back.
Could you repeat the question, Patrick?
Yeah, I asked how the fitness function also how the portion of the fitness function deals with not only being connected to one power pole, also the inserter in that problem, but also being connected to the power grid itself.
Oh, so we're going to have different fitness functions for each problem. So there's going to be, for example, you'll have a fitness function for the power pole problem. You'll have a different fitness function for making sure there's enough power and for where the inserters are being placed. And that's kind of where the interesting, real meaty part of the research is going to come in, is making decisions between which of the various fitness functions take priority, or if there's a hierarchy. So for example, if you want to create a base, that's a very abstract concept when you think about individual fitness functions, and how you decide what a good solution is really dependent on how each solver will solve that. And then you need to also weight those. So for example, if you can make a really nice base by putting all your resources into putting down 5,000 electric poles in a lovely grid, but you're out of resources and you can't do anything else, you might solve one problem to maximum optimality, but everything else would be 0%, right? So you need to weight those so that your solver doesn't just produce silly solutions that, provide maximum optimality for one and poor solutions for everything else. So that sort of consideration of the covariance in this summation across the fitnesses is going to be a large part of this project in the end. And to get there, we need to have all these problems defined and all these individual fitness functions defined. The way I see it hopefully happening is that we'll have, you'll have a sort of higher level abstract concept, like I want to produce iron plates, which is kind of abstract because you need to have power, you need to have belts, you need to have inserters placed, you need to have miners placed. So what's going to happen is the top level one will kind of be put on hold, and it will pass on a request to a lower level, like, okay, do we have iron ore, first of all? And then it'll say, okay, well, to get iron ore, we need to first of all have drills placed. And then that one will check if there's fuel. And it'll solve in this almost sequential but structural kind of way. That's how I envision this eventually that's how I eventually see this working. But all that's experimental and we don't know how it's going to work in the end. So we'll have to wait and see. Does that answer your question?
Yeah, kind of. I thought about a problem with placing electric mining drills, because I made a whole power pole solver. And if you would say place a few electric mining drills at once, you can't guarantee that every one of them can be connected to the grid. So you had
that
to place
depends.
one.
That depends. You could, for example, include in the electric drill placement problem, part of the fitness function could include space being left for poles. So that could just be inherently there. Or alternatively, you don't need to solve the whole problem. You, instead of having a big patch of ore this size and placing all of the drills, you could instead cut it down to a very small segment and placing a drill there then that calls the electric pole placement problem solver. It solves for that small place, and you do this over and over in tandem.
Yeah, exactly. That was what I thought would be a good solution for it.
Who knows?
Because
and that's
if you
that's going to be part of the research, right? I'm hoping that when we open this up we open up the FLE to other researchers, I'm hoping they'll try different things out. I'm hoping they'll look at this and say, I'm hoping one person tries machine learning on everything. Then I'm hoping somebody else tries this sequential one-by-one approach, and so on. The point is, I don't want us to try and solve that problem. Almost, I want to make this problem available for others to try to solve.
Okay, yeah, nice. So thank you for your both answers.
Any more questions for Payam? Okay, thank you all very much. Sorry, this meeting has gone almost twice the length I expected it to, but I think we had some interesting conversations throughout, which extended the length of it, which is not a bad thing. So this is, like I said, this has been recorded. I'll be putting this onto YouTube later today. Feel free to share it out as you please, and to friends, family, or whoever might be interested in seeing your presentations. That's absolutely fine. And I'll put a link into Slack so everybody can see it there too. Thank you for your presentations, all three. Can we have a virtual round of applause for them all? Much appreciated. And congratulations on passing your projects and everything, Patrick and Tom. That's excellent news, and I appreciate you coming back after you finished to present. That's really, really much appreciated. Okay, thank you all.